Hello everybody, welcome to the Math channel. Today I will be solving this problem. If n is a perfect square, then show that n in the power of 4 sevenths plus 4 sevenths n plus 1 is not divisible by 1155. So just for my audience, I just want to say that I didn't look into this problem before. I took this problem from the book called 25 Years of Mathematical Gazette Problem Corner. And I believe this problem is in some of the Mathematical Gazette from 80s. So I will try to just apply common sense, try to solve this problem, and then later I will look into the proper solution and check if my course of thoughts was actually correct and if I came to the right conclusion. All right, so let's start. All right, so we have this statement that a n in power 4 sevenths plus 4 sevenths n plus 1. So first thing, and then we need to check that a is not divisible by 1155. Because we have this like kind of weird numbers, it would be great to see the prime decomposition of those numbers, like the prime factors of those numbers. So for 7, 7, 7, 7, clearly we know it's divisible by 7. And I believe this thing should be divisible by 11. So yes, it will be divisible by 11. So prime factors of 7, 7, 7, 7 is 7 multiplied by 11 multiplied by 101. Let's find prime factors of 1155. So clearly it's divisible by 5. If you divide by 5, 1155 divide by 5, of course it would be 01. So I can see that 231 divisible by 3. So it should be 5 by 3 by 3 by something, which we'll find now. 23, 7, 21, 21, 7, 77. So it's basically 7 and 11. Okay, I think this is something. Basically, we need to check that a is not divisible by 3, 5, 7, 11 if n equals k squared. This is actually quite useful. Let's put this thing into the a, and we will get that a equals k 2, 7, 11, 101 plus 7, 11, 101 k squared plus 1. So this we need to prove that this cannot divide by 3, 5, 7, and 11. So my first thought how to approach this would be to check if it can be divided by 3, 5, 7, and 11 separately, and to see if there are any patterns there that we can see. Let's check divisibility by 3. All right, so like if k divisible by 3, which means k equal to 0 modulo 3, then obviously k in this power also equals 0, and then because we have k here, so like this thing k squared equals 0, so which means a equals 1 modulo 3, so it will not be divisible by 3. Let's check if k equals 1 modulo 3. This means automatically that k into 7, 11, 101 equals 1 modulo 3 because of powers, and then k squared equals 1 modulo 3, which means that the second piece, which is 7, 11, 101 k squared, equals 7, 11, 101, 1, which is equals 7 is equal 1 by modulo 3, 11, 2 by modulo 3, 101, 2 by modulo 3, and 1 by modulo 3, which equals 4 by modulo 3, which equals 1 by modulo 3. So what it means is a equals 1 plus 1 plus 1 equals 0 modulo 3. So actually we can see that like if k equals 1 modulo 3, then a is divisible by 3. This is an interesting pattern. We see like conditions in which this thing, which is a, will be divided by 3 when k is equals 1 by modulo 3. So what I suggest we'll do now, because we found like a case where it's divisible by 3, let's check. Let's check the same as we did with before. We check divisibility by 5. Okay, let's see. Let's see if a can be divisible by 5 at any point. Okay, it will require like a bit of more work. All right, let me think about it. All right, a equals I think it's useful. Okay, anyway, let's just do it like this: 2.271101 plus 71101 k squared plus 1. So we know that this thing is equals 7777. So like if it's like look into this, so this 7777 modulo 5 equals 2 modulo 5. Why? It's because 7775 is divisible by 5, right? So like we have only 2, and then basically it's 2 modulo 5. So basically a equals k to 71101 plus 2k squared plus 1 modulo 5, which is something, right? Here I'm thinking if we can apply a Fermat little theorem. So I don't know if it will be applicable, but let's try to look what's Fermat little theorem. So Fermat little theorem is saying that if P is prime and a integer such as a global common divisor of P and A equals 1, so they don't have any common divisors except 1, then A in the power P minus 1 equals 1 modulo P. Okay. So P is prime. P equals 5 is prime. We know that 5 is prime. In this case, we can apply Fermat theorem. It's basically saying that k in the power of P minus 1 equals 1 modulo P. Is basically k in the power of 1 equals 1 modulo 5 if k is not divisible by 5. All right, the k is not divisible by 5. K in the power of 4 equals 1. So let's find modulo 4 of this thing. 2, 7, 11, 101 modulo 4. What that would be? So 2 modulo 4 is 2. 7 modulo 4 is minus 1. 11 modulo 4 is minus 1. 101 modulo 4 is 102 is not divisible. What's the closest? Oh, 100 is the closest, so it's 1. So it's equals 2 modulo 4. So I use this like minus 1 modulo 4, which means that basically we know that 8 divides by 4, which means that 8 minus 1 basically equivalent to minus 1 modulo 4. This is why I use like minus 1 is just to simplify a multiplication, because minus 1 is easier to operate than like let's say 3 in this case, which is equal actually, right, in terms of like modular arithmetic. And please ask me questions under this post if something was not clear. Always happy to go and provide additional explanation. So basically what it says that k in the power of 2, 7, 11, 101 equals k for some t plus 2, which is equal k square modulo 5 by Fermat little theorem. But actually this is this statement. So by Fermat little theorem, like this piece is equivalent to 1 modulo 5 if k does not divide 5. So we like all here like if k does not divide 5, right? So if k does not divide 5, k does not divide 5, we have a few cases. So basically a few cases. K equals 1 modulo 5, 2, 3, 4, right? And then we will just like consider all these cases. So if k equals 1 modulo 5, then a is equals a key square plus 1. So in this case, if k equals 1, this would be equal to 4 modulo 5, same as minus 1 modulo 5. If k equals 2, equals 3, equals 4, so like this is like cases. So if k equals 2, so it will be 3 by 4 plus 1 equals 3 modulo 5. In this case, a equals 3, 9 plus 1, which is equals 3 modulo 5. In this case, a is equal 10 plus 1 equals 49, and this is equals 4 or minus 1 modulo 5. Okay, this is actually something. So let's consider case where k divides by 5. So k equals 0 modulo 5. In this case, a equals 0 plus 0 plus 1 equals 1 modulo 5. All right, I think this is something. I think we have proven that for any k, a is not divisible by 5, because in any situation, like if it gives a 0 modulo 5 or 1 or 2 or 3 or 4, we never get in resulting expression to give a 0 modulo 5. There is only minus 1, 3, 3, minus 1, and 1. So a cannot be divided by 5, which means a cannot divide by 3, 5, 7, and 11. And this should conclude the proof. So this should be the end. And now I'll take a pause and read the solution to this problem, and then I will get back to you to report if my solution was accurate. All right, now, so I have checked the official solution of this problem from the end of the book, and now we will get through it. So apparently my solution was not really far from solution here. This solution is simpler, is not using a Fermat little theorem, which I helpfully put here on the screen, so you can also familiarize yourself with invention of like this great guy Fermat. So let me remind Fermat little theorem, so like everybody knows really what we are talking about. So if p is a prime and a is any integer not divisible by p, then a in the power of p minus 1 equivalent to 1 modulo p. Okay, let's get back to the solution. All right, so if n is a perfect square, then n equals 0, 1, or minus 1 modulo 5. This is actually very easy to check. I think you can check it manually, or you can just trust it. Like, let's check it really quickly. So if it's n and then n square modulo 5, and let's say 0, 1, 2, 3, 4, n square 0, 1, 4 is same as minus 1, 3, 3, 9, which is minus 1, and 4, 1. So it's basically 0, 1, or minus 1 modulo 5. Then we mark Fn, n in 7777 plus 7777 n plus 1. Then f of 0, f from 0 equals 1 modulo 5. F of 1 equals 1 plus 2 plus 1 modulo 5. Right? Yeah, it makes sense. If you put 1 here, yeah, this equals 1, and then equals 7777. We know that 7777 equals 2 modulo 5. We actually use this result previously. And then f minus 1 equals minus 1 plus 3 plus 1 equals 3 modulo 5. Then Fn is not divisible by 5, which concludes the solution. Same as in my example, where I actually tried every single case of remainders of n divisible by 5. Here they did it very, very quickly. Indeed, this is a very neat solution. I think the key here was to actually reduce the space of considering only this 0, 1, and minus 1 as a space for n by using the fact that n is a full square. Great problem. So on this, thanks everyone for listening, and see you later. Bye.